before it goes.
1, 2. Okay, cool. Speak to you later.
Bye.
Thanks, mate. Bye. Hey, everyone. Welcome to year 13 maths. We are going to be doing maths every single day. I'm going to try and answer your most common questions at the beginning so that people can just scroll back to the beginning and see what we're going on about. But first, I want to see if I can share my iPad, because a minute ago when I was doing the first years, I couldn't share it, which was a bit of a pain. It didn't matter, but it would be better if I could share it. No, it's being weird again. Okay, right. I'll share my actual screen then, and you can just see what's going on in there. Where is it? Okay. Sorry about that. And then I'll just have to look at the chat every so often. So, common questions. What is happening? What is happening is we are doing at TT a just in case structured revision, like learning from home, supporting you with working through the next few months and weeks. I'll show you the schedule in a minute. The course that we're doing is free. It's called the Maths Exambulance, and you can get it on the Tailored Tutors website. So you go to the Tailored Tutors website, it says Exambulance, then you just click on the maths one and then you've got in. And I'll show you, that's where all of the resources I'm going to be using. I just realised I haven't got my glasses on, no wonder I can't see, but I don't know where they are. All of the resources I'm going to be using are going to be in the Exambulance, okay? Well, Ratib, you don't need to comment on the Exambulance because you've got a TT subscription. So what is happening? Today we're starting off, it's 1 o'clock, so we're going to be doing 1 o'clock second year maths every day, just in case, okay? Because the exams in September you may need to use. And if you wait to find out whether or not you're going to take the exam in September, then you are going to have about 5 or 6 weeks between finding out and doing it. And that will not be enough time to make up for 3 months of not studying. So you will actually get lower in that exam if you stop now and wait. So it's really, really important to just keep it ticking over. So it's based on 1 hour per day, 5 days a week, which I'll do with you from 1 till 2. I'll also be here from 4 till 5 every day doing a study with me. So if you're finding that the routine and the structure being lost is a bit difficult, then you can always come 4 till 5 every day. We'll all make a commitment what we're going to be doing for that hour. I will be answering questions in the TT course, and then we're going to really focus for that action hour, okay? How long is this live? It is 45 minutes. An action hour is 45 minutes and then an enforced break. So we're going to set a timer for 45 minutes and we're going to stick to it. We're going to have a clear focus. That's what an action hour is. And then at the end, we're going to have another timer for 10 or 15 minutes, and you have to take that break. Otherwise, you don't build up the benefit of the whole point of the action hour. Is this AS or A2? This is A2. Okay, this is second years. First years, I just finished. So the recording will be up whenever the recording is up. But this is for second years. First years come back tomorrow at 12. I'll be doing 12 every day as first years, 1 every day as second years. Which exam board is this? All of them. There is only a subtle difference between AQA, Edexcel and OCR. They legally had to have the same spec. So they are word for word identical. AQA, there are a couple of bits they're not assessing that Edexcel and OCR decided they were assessing, but that's the only difference. It's ladders and continuity correction in the second year mechanics and stats. That's it. Other than that, they are identical apart from the stupid large data set. So this is for all specs. It doesn't matter which. Can I ask about grades in uni and stress and stuff like that? Not in this action hour. We're going to come back at 6 o'clock for our normal Monday check-in, and we're going to be talking to you about what we found out from people that we know in teaching, people that we know in examining, and we'll let you know everything that we know, okay? What we are going to do today, right now, is we're going to start our schedule. So let me pull up the schedule from the Exambulance, and where is the Exambulance? Here. And if you haven't got the Exambulance, please get the Exambulance so that you can print out the things that we're using, okay? And anybody who doesn't know how to get the exambulance, just shout and we will show you how to get it. Is this downloadable? No. Okay, give me 1 sec. Actually, if Rich is, I'm just going to text Rich and ask him. Actually, Rich, if you are listening to me still, can you put a comment in the chat? Could you go on, hang on. Could you, Rich, if you're watching me, could you go in exambulance and make, what's that called? Schedule downloadable for maths. Hopefully he'll do that and a magic download thing will help here, will come here. So this whole idea is for just in case, okay? Because if you have an exam, if you find out that you are going to be doing that exam, look where we are in terms of time, right the way down here. So there isn't going to be enough time to make up for 3 months off. On the other hand, maybe you are absolutely fine and you don't need to do this study. So a compromise is an hour a day. And not only is it an hour a day, it's also an hour a day where you can just tune in and do whatever I'm doing with you. So it shouldn't be that stressful. It should be something that you can commit to future you just in case this schedule is for. There are 2 strategies. First 2 strategies are to properly finish all the content. So I'm going to find out from you today, and you're going to find out as well what it is you haven't done. And we're going to make really, really good, beautiful revision notes. They're in the revision notes section here. And we're also going to just make sure that everything you have learned doesn't start to fall out of your head. So that's strategy 2, using the TT method. We're going to sort of alternate them, as you can see on this schedule. Okay, when it gets to the end of July and you actually get those grades, then we will be working with those of you who are going to be taking that September exam to make sure that we then tighten it all up, put that extra push in and make sure that you can really, really crush it whenever that exam is, so that you can get the grade that you need. Okay, so we are going to be looking at the maths course map for Pure today, and we're going to be finding out what it is that you guys didn't do. And then at the end of this, you're going to let me know what main things you didn't do so that I can help you to learn them. Okay, so this is the map that I'm talking about. You don't have to print it out, but if you print it out, then it's easier because you can just highlight stuff and cross stuff off and that kind of thing. Okay, I need, oh, look, Rich has done it. He is listening. Hi, Rich, thank you. Brilliant. Isn't that, it's kind of like, it's great. You just speak out loud and then things are done for you. Rich is amazing. Okay, so here is it, all of the pure maths. By the way, I can't see your comments at the same time that I'm sharing this screen. I have to switch in and out. Well, actually, like you can see, I need to switch to this and then I can see your comments. So I'm going to be switching in and out of those. I'll have a quick look at the comments to see what you're asking about, but then I will switch back to sharing my screen so that you can see what I'm talking about. Okay, this is all of the pure. We'll just go across the top. The most important bits are in red, the least important bits are in blue. Okay, and I am going to put our timer on. This is our action hour. Action hours involve the following: a timer for 45 minutes, and a clear target. Our clear target is to read through all of the pure that's in the A-level maths and highlight what hasn't been done and decide what we're going to do this week in your sessions with me. That is our clear target. Ready? Go. Okay, graphs. All of these are in the first year, so I'm not going to be talking about it because you did learn all the first year stuff. Anything that doesn't have a circle around it is first year stuff, okay? So all of the graphs is done. There's no extra graphs in the second year, except for maybe this one, number 17. Now, this is called rational functions. Some first year teachers will have taught it because essentially it's a transformation of 1 over x, but it's quite a complicated transformation of 1 over x. And you don't need to fiddle around with algebraic division to make it find out what that graph looks like. If you imagine a reciprocal graph with the 2 asymptotes and then the thingies like that, imagine moving it up and left and squashing it. That's what they look like, but there are ways to find those asymptotes and stuff. So you might want to look back at 17. Algebra. Binomial expansion is the exact same. My method of teaching it is the exact same method for first years and for second years. If you've been taught binomial expansion, and what you've been taught is that you need a number 1 at the front, because otherwise you can't use the formula, that's a lie. You do not need a number 1 at the front, and pulling all the things out so that you've got a number 1 and then whatever sits at the front, oh, it's carnage. It's such a mess. So if you would like to see a much easier way of using the binomial expansion that works for any n, could be negative, fractional, positive, whatever, it's the exact same, then have a look at video number 8. The numbers here, they're the videos of the TT course that correspond to that topic. Okay, so each video is about 10 minutes. So binomial expansion, I haven't done separate for year 1, year 2 because they're not separate. You can use the same method. Algebraic fractions, I don't know why this is officially a second year topic. It's just adding fractions that have got x's and y's in and like timesing them and just mucking about with stuff. Usually factorizing stuff out on the top, factorizing stuff out on the bottom, cancelling factors, that kind of stuff. Partial fractions, you'll know whether or not you've done this. It's where you've got a fraction and you're unadding them. So instead of having this add this and you're bringing them together into one fraction, you've got one fraction and you're pulling it apart into 2 separate fractions added up or unadded. So that's what partial fractions does. Partial fractions is never ever a question on its own. It's always part A. Part B will be either the binomial expansion or integration. So the partial fractions here, they link to binomial expansion and they also link to integration when you're integrating fractions. So that's when we use them. Really, really important to check that they're right before you move on, because if you do your binomial expansion bit or you do your integrating and you've made some silly slip with the partial fractions, that's all your accuracy out the window. It's very frustrating. Okay, trig. This is the big one. This is huge, okay? If you do not know your trig identities inside out and back to front, then you are going to lose a lot of marks, particularly around the differentiation and the integration, and also, particularly the differentiation and the integration. So trig, even though it is a separate topic, if you have a look at how much of differentiation is actually trig and how much of integration is actually trig, you'd be amazed. It's really, really important. So small angle approximations is a kind of separate thing. You may have done this or not, so tick it if you've done it. If not, highlight it as needed to be done. So if I'll tell you roughly what it is, and then if you don't know what I'm talking about, tick it off. So sine x is more or less x if x is small. Tan x is more or less x if x is small. So we can just replace sine x with x. We can replace tan x with x. Cos x is more or less 1 minus a half x squared if x is small. So we can just replace cos x with 1 minus a half x squared. Now, if that rings a bell, that means you've done small angle approximations. There's nothing more to it other than that you have to be in radians. And if you don't know what I'm talking about, then highlight that one as something that needs doing. Now, I cannot believe that anyone in the country, no matter how bad the teaching plan is, doesn't know what sec, cosec and cot are by this stage, but you should also be able to sketch them. So sketching sine, cos and tan, sketching sec, cosec and cot, and transformations of them is something you could get asked about. Now, sketching arc sine, arc cos, arc tan, that's more, these are inverse functions. So if you look in the bottom left where it says inverse functions here, it's just an example of sketching inverse functions. So it's exactly the same as sketching the inverse of any other function. It's a reflection over y equals x, and we restrict the range so that it's a one-to-one function. So all of the stuff that you learn over here in functions applied to trig is what you see here, arc sine, arc cos, arc tan. You might need to solve some very simple equations, like what is arc sine of cos of pi by 3? Or what is tan of arc sine of a half, or something like that. So video 18 is the one that you need for that. Where does it say 18? It doesn't, does it? That 10 there should not say 10, sorry. That's 10, or maybe it does say 18, it's just really small. It does, it's 18. Okay, it's 18 for the inverse trig. Right, trig identities. Number 1, Pythagorean. Sine squared x plus cos squared x is 1. Okay, 1 plus cot squared x is cosec squared x, and tan squared x plus 1 is sec squared x. Does that ring a bell? If it rings a bell, just tick it off. You've done it, okay? Maybe we need to revise it, but you've learned it. Next, sine a plus b is sine a cos b plus sine b cos a. Cos a plus b is cos a cos b minus sine a sine b. Tan a plus b is tan a plus tan b all over 1 minus tan a tan b. Is that ringing bells? If so, tick it off. You've done it. Those are the addition formulae. Double half, cos 2x equals 2 sine, no, sine 2x equals 2 sine x cos x. Sine 2x is 2 sine x cos x. Cos 2x is cos squared x minus sine squared x. Tan 2x is 2 tan x over 1 minus tan squared x. Does that ring a bell? Sine 2x, cos 2x, tan 2x. If so, tick that one off. You also get these 4 extra doubly halfy ones. So cos 2x, that's a special one. Cos 2x is cos squared x minus sine squared x. But we can replace the cos squared x with 1 minus sine squared x. Or we can replace the sine squared x with 1 minus cos squared x. So we get these 2 bonus ones. Cos 2x is 2 cos squared x minus 1. And cos 2x is 1 minus 2 sine squared x. And both of those rearrange really nicely. So the first one, cos 2x equals 2 cos squared x minus 1, that rearranges into cos squared x equals. And we use that in integration all the time. Can you see here? It says integrate cos squared, integrate sine squared. The way you integrate cos squared and sine squared is using this formula that I'm talking about now. So cos 2x is 2 cos squared x minus 1 rearranges into cos squared x is a half 1 plus cos 2x. And that's how we integrate cos squared. If you write cos 2x as 1 minus 2 sine squared x, you can rearrange that to say sine squared x equals a half brackets 1 minus cos 2x. And that's how you integrate it. How do we integrate tan squared and cot squared? We come back to our Pythagorean identities. So tan squared x is sec squared x minus 1. And we just change that tan squared to sec squared minus 1, and then we can integrate it. Cot squared is cosec squared minus 1. That's a Pythagorean identity. So we just swap it out, and then we can integrate it. So these really, all of these come in hugely when you're integrating. Really, really important. Now, you could practice doing trig proofs and solving trig equations every day from now until the exams in June 2021, and you still might get a trig equation or a trig proof that you get stuck on. You build skills, you build confidence, but that's what you're doing. You're never done with it. It's never understood and done, whereas almost everything else in the math syllabus, the only other thing is vectors, where you can't just learn it. Everything else is just learnable and practicable. And if you practice it enough, then guaranteed you'll be fine in the exam. But integration, trig proofs, vectors, you have to just build skills, develop those skills. So when I'm doing this hour with you each day, we're going to be doing 1 till 2, an action hour. I'm going to make you do integration every time. So right at the beginning, we'll just integrate a few things so that we're keeping that integration ticking over. And that in itself is going to practice your trig, and it's going to practice your differentiation. So by doing the integration, we are covering the trig, we're covering the differentiation, and we're building up those really strong skills. This is what should be done in September. And I fear many of you started this very recently, stroke not at all, because it's at the end of the book. Why people teach in the order of the book, I will never know. It is ludicrous as far as I'm concerned. So we are going to be really focusing on the integration. Even if you've all done it all, we're still going to be doing it, because if you're going to take that exam in September, then you need to be building up your stamina with integration. Okay, let's finish the trig. R cos x plus a, harmonic form this is called. This is where you've got some sines and some coses. I might have 7 sines and 4 coses, or I might have 2 coses minus 6 sines, or whatever. I've got some sines and some coses, and what I want to do is merge them together to make one trig function. Some sines, some coses, in they go together to make just a cos function or just a sine function. You need to know how to find the r, and that's the 2 numbers Pythagoras. Is that a verb to Pythagoras? So, you know, I said, like, say I've got 6 sines and 2 coses, then the r is 6 squared plus cos 2 squared square rooted. And if I've got like 1 sine and 4 coses, it's 1 squared plus 4 squared square rooted. So it's easy peasy. The a is a little bit more difficult, but not really. So you'll know whether or not you've done this. You'll know whether or not you've been shown how to find the r and how to find the a. Now, why do we do it? What's wrong with having some sines and some coses? What's wrong with that? Surely it's nice to have some sines and some coses. Well, solving equations is a bit of a pain. Imagine you've got some sines and some coses equals 2. How are we going to solve that? Can't make it tan. Can't divide through by cos because it wouldn't work, would it? Because the cos divided by cos would be 1. Sine over cos would be tan. So we'd have a 1 and a tan. But then the number on the end over cos, that would be a sec. Doesn't work. So solving equations that have some sines and some coses, much, much easier to go into harmonic form. Also, maximums and minimums. If I have 9 cos bar, blah, 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 9 cos, blah, blah, blah. The highest that goes is 9, the lowest it goes is minus 9, obvious. But if I have 4 sines and 2 coses, I don't know what the biggest is. It's not 6 because I can't make the sine bit 4 and make the cos bit 2 at the exact same time because different angles make them maximum. So it would never go as high as 6, but how high would it go? So solving equations, finding maximums and minimums, that's why we do it. Now, you might think, I know how to find R and A, but I can't find maximums and minimums, I don't get it. In which case, tick off number 17. Or you might think, actually, I mean, I need to revise it, but I've done it, in which case, just you can cross that one off, it's done. Okay, I'm going to have a quick look at your comments in case you're asking questions. Have you asked me how to integrate something? Tan to the 4x. Yeah, tan to the 4x is nice. Actually, oh look, I've made infinite YouTubes. That's cool. Tan to the 4x is an example of this one. I will show you. Where's the map? Tan to the 4x is an example of this. Okay, it's an example of that. You can just literally, tan to the 4x takes 0 work, none, like half a second, and then you can just write down the answer. If you've done integration since last October, if you've been integrating all year and you integrate and integrate and integrate and integrate, then you can just see your way into things. You can just see what to do. So I'm going to come back to the integration. It is a really, really important thing. I'm going to be doing it with you every day. I'm going to be making you a playlist to watch especially. It is the thing that I think I can add the most value to for a lot of you in terms of the way you've been taught the A-level. Because if the integration was left to the end of the year, it's very, very hard for you to teach yourself that, almost impossible. And doing it quickly is also absolutely, like, it's a recipe for disaster. So I'm really focused on supporting you guys with the integration. Okay, let's have a look at the geometry. So the only other bit from the geometry that isn't in the first year is arc length and sector area, which are measured in radians. So you need to know what radians are, how to convert from degrees to radians, and you need to know these two formulae. Sector area, this bit in a circle, is half r squared theta, and the arc length of a sector in here in a circle, that arc length is r theta. You can also, by the way, a lot of people think that it's only the minor sector and the minor arc that we can do that for. And you see students making it really complicated in exams. So say you have a whole circle and you chop out a sector, or you take a piece of the cake and you want to know the area of the rest of it, or you want to know the arc length of the rest of it, you can still use these formulae. It's just the angle is obtuse. The angle is like, I don't know, like 11 pi by 12 or something. So half r squared theta is sector area. It could be the minor sector or it could be the major sector. And r theta is arc length. It could be the minor arc length or it could be the major arc length. Still true. Right, that's geometry. The rest of it's all first year stuff that you should be okay with. Right, moving on. Your aim, don't forget, for this hour is to have a really clear picture list of what you haven't yet done so that I can teach you it. Okay, and I'm going to stay supporting with you until you've got it all sorted, until we can look over this page and just tick everything. That's our aim over the next couple of weeks. But for today, we're just doing identification. Right, functions. So there are three main types of functions that you need to be able to work with, and then there's functions in general. So the functions you need to be able to work with: exponentials, that was all covered in the first year, but you might have forgotten, particularly the linearizing data, you might have forgotten, but that was all first year stuff. That's one type of function, exponential. Another type of function is modulus. These are weird beasts, modulus functions. Students think they get it. The modulus ones are the ones that look like a V, and you move them around, maybe you have one and then another one and do their cross and stuff like that. Students tend not to say they need help with modulus functions until they do a past paper. And then over and over and over, it's the modulus questions that they get wrong. So don't underestimate the depth of that particular topic. Yes, they are just a V shape. Yes, you do just bounce the bottom bit up to get a V, but then the problems that you solve are, you have to really get what a modulus function is, not to just go really horribly wrong. So that might be one some people need to tick off or do some more work on. Parametrics, I know lots and lots of people haven't done. So there is parametric equations are like x equals cos t, y equals 3 sine t. So you get x is something and y is something. And then you generate an xy coordinate from an individual t. So I know lots and lots of people haven't done that. In particular, what do we need to be able to do with them? You don't need to sketch them. You need to be able to change them into Cartesian. Cartesian is x's and y's. So you need to know the tricks for getting a parametric equation and turning it into a Cartesian equation. You need to be able to differentiate them to find the gradient of the tangent at a particular point. And you need to be able to integrate them to find the area under a curve. So those are the things you need to be able to do: differentiate, integrate, convert. So tick off anything that you haven't done, or highlight anything that you need me to teach you. It might be converting, it might be the differentiation, or it might be the integration. Then you've got this general sort of function stuff. So not a specific type of function like exponentials, modulus, parametric. This is just general function stuff: range and domain, composite functions, inverse functions, building and using composite functions, building and using inverse functions. And then domain and range, I'm sorry, but for range you have to draw a graph. Yes, you do. You have to. There are, just think of it as range, graph, same. If I say what's the range, I mean draw the graph, what's the range. That's what I mean by range. So if you haven't done that chapter yet, that is definitely something we need to cover, but it is quite standalone, to be honest. Look at it all on its own on the left-hand side, just sitting there with a little box around it. It's not a big deal. It's not, say you can't do it, right? Say I don't teach you range and domain, composite and inverse. Then there will be one question with some bits that you can't do. That'll be it. The whole other 295 marks of the A-level will be fine. It just will creep in somewhere, that's all. So not a big deal, but if you want me to teach you it, then highlight it and let me know. Okay, I'm going to jump over to vectors, and then we'll do the big two, the differentiation and the integration. We've got 24 minutes left of our action hour. When the timer goes, we stop, even if we're mid-sentence, for 15 minutes before you're allowed to start again, or 10 if you're really keen. Do the break. Honestly, it works. You would not believe how much more work you get done in a day when you're using action hours. It's incredible. Now, vectors, right? I know that they're hard, but they're not hard because they're in 3 dimensions. They're hard because they were hard last year, but you didn't do enough practice of them because they're at the end of the book. That's why. So the only difference between first year vectors and second year vectors, literally the only difference is that in the second year, there's a third dimension. So in the first year, you've got i's and j's. And in the second year, you've got i's, j's and k's. So in the first year, you've got in your column vector 2 numbers, and in the second year in your column vector you've got 3 numbers. That's the only difference. You still find the length using Pythagoras, okay? You still find the angle between vectors using the cosine rule by drawing a triangle, finding the length, finding the length, finding the length, doing the cosine rule. You still work out if vectors are parallel by seeing if one is a multiple of the other. You still make a unit vector by dividing a vector by its length. You still prove that things are a square by showing that there's one right angle and that these two are parallel and these two are parallel and the same length. You still do a square in the same way. You still prove that something is a trapezium in exactly the same way. Zero difference. So I have made a video, it's number 12, on 3D vectors, but honestly, there is nothing about 3D vectors that is any different from 2D vectors, other than that you can't find the direction they're going in. Because what do you mean? Do you mean the angle to the ground, or do you mean the angle to the x-axis, or what angle? Even, to be honest, even first year direction is a bit of a silly question. Like, what direction is that going in? It's going that way. Like, what do you mean? Do you want that angle to the north, or do you want the angle from there down, or do you want to know, like, it's a silly question. It's a silly idea, really, direction. You know, to be isolating direction from a vector. Yeah. Anyway, I'm happy to help you with vectors, but bear in mind there's nothing new in there. Right, the big two. This is all you need to know. If there's a circle around the number, it's a second year topic. If there's no circle, it's first year. The number corresponds to the lesson in the TT content guide. Differentiation. You have to know the derivative of these 10 things. The derivative of e to the x is e to the x. The derivative of a to the x is a to the x ln a. The derivative of ln x is 1 over x. The derivative of x to the n is n x to the n minus 1. Derivative of sine is cos. The derivative of cos is minus sine. The derivative of tan is sec squared. The derivative of sec is sec tan. The derivative of cosec is minus cosec cot. And the derivative of cot is minus cosec squared. You have to know those. You also need to know that those 6 trig ones, sine goes to cos, cos goes to minus sine, tan goes to sec squared, etc. That's only true in radians. If you're differentiating or integrating a trig function, you have to be measuring the angle in radians. Otherwise, the derivative of cos is not minus sine. The derivative of cos is only minus sine in radians. Equation of a tangent and a normal. The only difference between the first year and the second year here that you need to be aware of is that your function that you get in the second year might not be y equals. So I might give you an implicit function. I might say x squared plus 3xy minus y to the 6 is 0. Okay, what's the equation of the tangent at the point x is 0, y is 1 or something? So I still want the equation of a tangent, but the thing you have to differentiate in order to get the gradient of the tangent is implicit. Or maybe it's parametric. Maybe I say x is cos t, y is 3 sine t. What's the equation of the tangent at the point t is pi by 6? So it's still tangent, it's still normal, but you have to be able to differentiate different types of functions. So implicit and parametric are the main ones. You also need to be able to differentiate things using the product and quotient rules. Product rule differentiates UV. I don't think of it as a formula. I think of it as 2 things together. U weight, I'm differentiating you at the moment, and then a plus, and then U weight, I'm differentiating you, now it's your turn. So they take turns to get differentiated. Quotient rule for differentiating a fraction. If you've got u on the top and v on the bottom, that's v du minus u dv over v squared is the derivative of the equation of the derivative of the function, of the fraction. So hopefully you've all done that, product and quotient rules. Chain rule, oh my goodness, I cannot tell you how important the chain rule is. The chain rule, with the first years, I'm doing, did I pull up the, no, I didn't. With the first years, I'm actually going to be doing the chain rule with them in June. If they hang out with TT this summer, I'm doing the chain rule with them in June because it is so integral to everything you do. I'm going to be doing some most important A-level topics just in case when they start September, there's disruption and their teachers get behind. So what I'm doing with them there is look, reciprocal trig, derivatives, chain rule, trig identities, integrating fractions, all of this stuff is absolutely core to getting a high grade in maths. I don't know if you can actually see that. I think I clicked on it, but didn't change my share. So I think that you don't know what I was pointing at. Let me just have a quick look at the comments to see what you're saying. Okay, you're helping each other out. Good. Okay, let's finish this off and then you can tell me what it is that you want the help with so I can plan the schedule for this week. Differentiation. Stationary points, derivative is naught. Maximum, derivative is naught. Second derivative is negative. Minimum, first derivative is naught. Second derivative is positive. You learn that in the first year. Inflection points, nothing to do with dy by dx at all. It's to do with d squared y by dx squared. If d squared y by dx squared is negative, then it's naught. If d squared y by dx squared is naught, then you have an inflection point if the second derivative changes sign either side of naught. So if the second derivative is like a quadratic and it comes down positive, 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 naught, positive, 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 that's not an inflection point. If the second derivative goes positive, 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 naught, negative, 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 then it's an inflection point. Inflection points are where the graph goes from convex to concave or vice versa. Highlight that if you don't know what I'm talking about. You need to be able to do first principles with sine and cos. First principles is the limit as h tends to naught of f of x plus h minus f of x all over h. You should know what that is from last year. You need to be able to do that with sine and with cos. If you should all know what I'm talking about, but if you haven't learned that yet, then highlight that. Now, derivative proofs. This is lesson number 28 in the course. Basically, you're expected to be able to prove the following derivatives, not e to the x. You don't need to prove that e to the x differentiated is e to the x, but a to the x, you need to be able to differentiate to get a to the x ln a. Ln x, you need to be able to differentiate to get 1 over x. I mean, prove that the derivative is 1 over x. Sin x and cos x, you would use first principles. Tan x, you would use the quotient rule, write it as sine over cos and use the quotient rule. Sec x, you could use the chain rule or the quotient rule. But all of these derivatives, all of them apart from e to the x, you are expected to be able to prove why the derivative is the derivative. Okay, so that's what that's referencing there, derivative proofs. Chain rule we've mentioned, ridiculously important. Chain rule tells you how to differentiate things inside things. I really hate the use of u equals. I've never seen it help students. So a lot of people teach, say for example, we were differentiating sine x squared. They would say, write u equals x squared. Then find out what du by dx is. Then go back to your sine x squared and write sine u. And then differentiate that with respect to u. And now you've got dy by du, and you've got du by dx. And now we're going to merge them together, and that's what the chain rule is. Oh my goodness. Number one, that's so overcomplicated, it's ridiculous. Number two, if you do that for the chain rule, you're never going to be any good at integration, because integration is the backwards chain rule. And if the chain rule takes you that long and you have to introduce the u, integration will always be awful. And my third reason that you shouldn't use it is, for example, it's a shame I can't share my iPad and write, but e to the sine x squared or e to the sine squared x. How do you what's the derivative of e to the power of sine squared x? Now, if you don't use u, if you use the way I teach, where it's just times by the derivative of the thing, then that's easy. But if you use u, it gets disgusting. It gets so horrible. So I really recommend that you go back to the chain rule, have a look at the way I teach it, it's in number 22, and just see if you can start to think in that way just a little bit. If you use the u equals, this is just a recommendation that you don't use the u equals. And the reason is not because of the chain rule, although it does come in there. The reason is more that the whole of integration becomes difficult if you use u in the chain rule. I hope that makes sense. Okay, differentiating x equals f of y. This is implicit differentiation, basically. Implicit differentiation is where you differentiate like x squared plus 3xy plus 2y to the 6 minus 4 is 0. So you've got this like bunch of sines and causes equals a number or something, or even like bunch of sines and causes equals, but not sines and causes. Did not mean that. X's and y's. Bunch of x and y's equals other thing, maybe numbers or bunches of x and y's. And you have to differentiate all the way across. So instead of getting dy by dx equals, you get some x's, you get some y dy by dx's, you get some more dy by dx's, you get a number, you pull together all the dy by dx's, put them there, factor them out, divide that thing under, and now it says dy by dx equals. That should ring a bell if you've done implicit differentiation. If not, that needs doing. Parametric differentiation is just the chain rule, literally. Connected rates of change is just the chain rule, literally. Differentiating x equals f of y is just the chain rule, literally. Depends how you're taught the chain rule. But if you're taught the chain rule in a way that's understanding rather than with this u thing, then all of these just become straightforward. They don't even need any teaching, really. Connected rates of change is where you've got like a balloon being blown up, and as time goes on, the radius is increasing and the volume is increasing. So there's these two things that you could measure that are both increasing or both decreasing. That's the connected rates of change. Integration. Okay. There are loads of ways of teaching this, but basically you need to be able, you only integrate 10 things, ever, I promise. At the end of the day, you only ever integrate sine cos, sec squared, cosec squared, sec tan, cosec cot, e to the x, a to the x, 1 over x and x to the n. That's it. All of the things that we do are just trying to turn them back into that thing there. So for example, the one that I saw earlier on the chat, tan to the 4. Write tan to the 4 as tan squared brackets sec squared minus 1. Tan squared brackets sec squared minus 1. So you would then have tan squared sec squared minus tan squared, and tan squared you can change to sec squared minus 1, and then boom, that's done because we integrate sec squared. And then tan squared sec squared is one of these. It's just tan cubed. The integral of tan squared sec squared is a third tan cubed, done. So if you spot these and if you know these really well, integration becomes a lot easier. I'm going to work with you a lot on integration. You need to be able to integrate sine squared, cos squared, cot squared, tan, and cot. You need to just know what to do with those ones. Just be fact what to do. You need to be able to use partial fractions and division from up here in order to integrate fractions. You need to be able to do integration by substitution and parametric integration. They're the same thing. So if you'll know whether or not you've done integration by substitution and integration by parts. Parts is a cute little formula. Students try to use parts all the time. You give them anything that's got two things in, students are like, whoa, parts. And it's usually not parts. So it's not just that you use parts for things times together. It's not a product rule. How do we differentiate things times together? Product rule. How do we integrate things times together? Depends, probably not parts. Solving differential equations is, well, there are 2 steps and then it just becomes integration. So it's called separating the variables, separation of variables. It can be really messy algebraically, quite heavy algebraically. Lots of, like, you have to be able to manipulate algebra quite fluently in order to not go wrong. But in terms of learning, it's just integration. If you could integrate, it would take me 2 seconds to teach you how to do differential equations. So it's basically differentiation. And then obviously there's the usual areas under curves, malarkey that you did last year, but now, like same as here, equation of a tangent and normal, same as the first year, but now the functions you need to differentiate are much harder. Same here, areas under graphs, same as last year, but now the functions you have to integrate are much harder. Okay, right, bottom three, we've got 9 minutes. Bottom three, these are not a big deal, right? If you haven't done these yet, great, your teacher did a really good plan for the year, because these are easy, they're not worth that many marks, and they're algorithmic, and we can do them pretty quickly, and they're not a big deal. The big deal are the red ones. Blue, it's fine, whatever. So there's numerical methods. That's where we can't properly solve the equation, so we're trying to find an answer to a few decimal places. Maybe it's an equation, like something is naught, or maybe it's a turning point, derivative is naught, or maybe it's when two graphs are crossing each other that we want to find, but we can't solve the equation analytically, we can't rearrange it and get the answer. So we can use a change of sign method and iteration to find an approximation of the root. So again, you will know whether or not you've done Newton-Raphson. It's a really simple method. You find the equation of the tangent, you see where it crosses the graph, iterate. It's a formula. Xn plus 1 equals Xn minus, and then a fraction, f of Xn over f prime of Xn. You'll know if you've done it. It's really quick. It takes 5 minutes to learn. Probably my video is probably 5 minutes. It's not a big deal. Same with the trapezium rule. Trapezium rule is the way of approximating the area under a curve. So you often see it combined with this in a question. Part A, trapezium rule. Part B, now integrate it and find the actual area. What's the percentage difference or something like that. So trapezium rule, rough way of finding area under curves. Newton-Raphson, a rough way of finding the root of a function where it equals 0. Proofs. Oh, that means, I was like, what? That means proofs of the trapezium rule and the Newton-Raphson formula. So that video 41 explains to you where that Newton-Raphson formula comes from and where the trapezium rule formula comes from. Change of sign is where you say the function's gone from positive to negative, so there must be a root because the function's continuous. Iteration is where you just keep putting it back in over and over and over, and it takes you to the root. And cobweb and staircase diagrams are the ones where you draw y equals x and you draw the other one, the one that you're using for your iteration, and then you can show how the iteration, when you put it back in and put it back in and put it back in and put it back in, you can show how it zigzags its way in towards the actual root. So it's a way of seeing the convergence of the sequence towards the root. The only extra thing you need for proof is proof by contradiction. Now, proof by contradiction is not easy at all, but it is not worth a lot of your time. It is one question, and it will basically be either the proof that root 2 is irrational, the proof that root 3 is irrational, the proof that there are infinitely many primes, or something very, very similar. So if you just memorize the root 2, root 3 and primes proof by contradictions, then you'll probably be fine. But it's not worth worrying about. Sequences. Arithmetic sequences, geometric sequences. Arithmetic ones are ones where you go add 2, add 2, add 2, add 2. You probably did them at GCSE. So you get given a little puzzle. The fourth term is 501 and the sum of the first 16 terms is 31. What is the third term? They're all pretty much like that. If they do try and put it in context, it's always somebody with a savings account, always. Sometimes there's this weird one with someone building a shape and it's like they keep adding 2 more matchsticks in. I mean, I don't know how long we would have to be in isolation before we got so bored we started making shapes out of matchsticks and then thinking, oh, it's an arithmetic sequence because I always add on 2 matchsticks. And then, oh, I wonder how many matchsticks there will be in my 15th. No one, like, but so they're not particularly exciting problems, but they're all pretty much the same. And there's only 2 formulae to learn for arithmetic sequences and 3 formulae to learn for geometric. Geometric is where you go times 2, times 2, times 2. So bank interest rates, for example. You do need to understand sigma notation, and recurrence relation is where it's like un plus 1 equals 3un. So you might have done this chapter in the book. It's just one chapter you might not have done. If you don't know it, then we need to fill it in, but it's not a big deal. Okay, we have got 4 more minutes and we have to stop when this stops. What I would like you to do is to have a look at I'm going to stop share, have a look at that thing we've just been talking about and decide which ones, please only choose 1 or 2 for now. We're going to come back to this, but which 1 or 2 would you like me to do tomorrow? So tomorrow at 1 o'clock, we will work on whatever is the most popular, okay? I'll read through the chats afterwards when we finished. So of those, we've got graphs, we've got algebra, we've got trig, geometry, functions and exponentials and things like that, modulus, parametric, differentiation, integration, vectors. There is also proof and sequences and numerical methods, but they're less important. Okay, so just chuck in the chat what you would like me to do tomorrow, and I will have a look at what's put in there, and then tomorrow we'll make a decision what we're going to do. Okay, so people haven't done numerical methods and sequences. Well, I think to be honest, we should focus on our aim. If you have a look at our study schedule, our aim for the next couple of weeks is to finish the content so that everybody feels a bit more confident on what they actually need to learn. So I think the best thing, if we look at the schedule, what did I put in the schedule? So I've put derivatives and inflection. Oh no, derivatives and inflection, connected rates and implicit differentiation, integration and parametrics is what I guessed for this week. I did those earlier than where did I put? I don't even know where I put other stuff. Did I even put things in? I don't think I put in sequences or hypothesis testing. Sorry, I'm tired now. I don't think I put in sequences or numerical methods because you can learn them so easily yourself. Honestly, either you've got the TT course, you can watch the videos, or you can just Google it or use the textbook. The sequences and the numerical methods, they're so straightforward that you kind of don't need me. But the important stuff, the integration, the differentiation, the trig, the functions and graph sketching to an extent, I think is where I'm going to become more useful. So it's up to you though. What would you like? Okay, modulus definitely I think is important. Parametrics I know lots and lots of people haven't done. Okay. All right, I think then what I'll do for this week is I'll leave the schedule as it is. It's got parametrics in, but we can do a nice review of differentiation and look at the integration. Okay, Luca, I'll have a look at comments now, literally in 1 minute. Raseb, that's a total waste of time, all the proofs you need to know. Honestly, the amount of time it would take you to do is this big, and the amount of marks it would get you is that many. Okay, total waste of time. Don't do it. It's like often we have a row, you and me, because what you want to do and what you put your time into doesn't make you any better. And then you do a test and then you go, oh no, I worked really hard and I'm no better. And I'm like, yeah, I told you, don't do that. Don't do it. Listen to what I'm saying. Okay, yes, I know a source where you can find all the proofs, the TT course, but honestly, waste of time. It's not a good use of time, honestly. Right. It is the end of our action hour. Well done, all of you, for turning up. I am going to go into the course now and answer questions. And I will hopefully see you either today at 4 till 5 for an independent study hour, but I'll be doing study with me. I'll be working as well, answering questions in the course, or 6 o'clock for our check-in to talk to you about what we've heard today about the September exams, about the teacher predicted grades, about the possibility of, you know, how this is going to pan out and what the appeals process is going to be like. And then tomorrow at 1, so 12 o'clock till 1 for first years and 1 till 2 for second years. Our timer has gone. We must stop. Okay, get away from your computer for at least 10 minutes. I'm going to do the same. In fact, I'm going to do 15. Okay, so you now must step away from the computer and stand up and move around. if you want to make the most of your study time. Okay? Get the exam balance if you haven't got it already, and I'll see you later.